Hey boys and girls, today we're going to go through and talk about solutions and kind of lead into talking about acids and bases, which are going to be the basis of this fifth unit and our final unit of chemistry. So you should remember the word solution just a little bit from unit 1, because a solution realistically is just a homogeneous mixture. And what that really means is that it is a mixture that has the exact same density, the same composition, the same color, and even the same taste throughout. So what we're saying is that being a homogeneous mixture, it is completely evenly mixed so that every single portion is, or every single sample is going to be identical. All right? So when we go through and we actually think of solutions, we know that they're made up of two parts. So as I was saying, solutions are made up of two parts. Your first part is going to be the solute, which is the substance that is being dissolved. Now, generally we can go through and we can dissolve almost anything. Yes, there's some things that are incapable of being dissolved, but we're going to focus on those things that can be dissolved. Those are going to be your solute. So if we're talking about sugar water over here, the solution itself is sugar water. Your solute is the sugar. Okay, which means examples could be sugar, salt, Kool-Aid, tea. You can dissolve carbonated beverages, have carbon dioxide dissolved in them. So you can dissolve solids or gases. Your second thing that happens to make up, or your second part, is going to be your solvent. Okay, and the solvent is the thing doing the dissolving. And we are always going to, in this class, consider water as our dissolvent. Water is considered a universal solvent because it will dissolve essentially anything. So the solvent is going to be the water, the thing that's doing the dissolving. The solute is the thing that you are adding and trying to get perfectly mixed into the water. Okay. Now, how does this dissolving process work? Well, this kind of kicks back to the idea of the kinetic theory of matter, which we've touched on a couple of times in this class. You should remember that all matter is made up of very tiny particles. Those tiny particles are in constant random motion, always moving around, and because they move around, they're going to collide frequently with other molecules, other atoms, or the sides of the containers. Well, when we dissolve sugar in water, basically what's happening is the water molecules and the sugar molecules are constantly moving around and they start colliding into each other. And what happens is the water molecules will actually attach to the outside of the sugar molecule and start to break the sugar down from the outside in. So what that's saying is that we go through and you are going to have your sugar molecule can only get dissolved from the outside. I can't start breaking down sugar from the inside of the molecule or from the inside of the sugar. It's got to work its way from the outside inward. So basically it can only attack the surface. That's kind of something we'll get into in a second with how we can speed up dissolving. Because while the dissolving process is important, sometimes you want something to dissolve in a faster manner. And we've got a couple ways that we can go through and actually speed that up, and we'll get into that in a second. So, in the dissolving process, we know that the solvent, in this case water, is working on the outside of the solute. So whether we're talking about salt or sugar or tea or whatever, it's working on the outside of that object to break it down. And as it breaks it down, you're going to increase the amount of space that the water can actually work on. Notice that in the first picture over here, the water can only work on this outside region. But as soon as the molecule gets broken down and starts dissolving off, you can now attack all of the outside. Okay, and this should make sense to you if you think about the last time you had a lifesaver or something like that. When you go through and you can maintain keeping it whole in your mouth, it will dissolve shrink in size very, very, very slowly. But as soon as you chew it, you've increased the surface area, and that's going to dissolve in your mouth much, much, much faster. So realistically, what's happening is it's working from the outside. So how do we go through and we increase the speed that things dissolve? Well, we've talked about one of them, but your big major goal here to increase dissolving is by increasing collisions. Okay? Increasing collisions. And that was also the way that we increased chemical reactions, if you recall from Unit 4. So we want to increase the collisions between the solute and the solvent. And if we can increase collisions, your molecules will dissolve faster, or your solute will dissolve faster into the solvent. And the three ways that we can do that realistically are going through and stirring, because as we stir, we go through and we increase the speed of both the solute and the solvent, which means we increase collisions. As we increase the temperature, we go through and we increase the dissolving rate because the molecules are moving faster as the temperature increases, and that means for more collisions. And you should kind of have an understanding that hot can hold a lot more than cold. So if you want to go through and dissolve a lot of tea or bouillon or salt or sugar into water, cranking up the temperature means that that same amount of water will be able to hold more of the solute. And then the third one, the one we just kind of talked about, is increasing the surface area. If you have more surface, you've got more chances of collisions because there's more space for the solute and the solvent, more surface area space, for those collisions to occur. So if you can go through and make smaller pieces, it's going to increase how quickly something will dissolve. And your example there would be like sugar cubes versus sugar granules, or chicken bouillon cubes versus chicken bouillon granules. If I go through and I have a set square, cube, okay? If I have one of those, it's going to dissolve a heck of a lot slower than if I just have tons and tons and tons of little pieces of sugar. Okay, so going through and having smaller pieces will increase. This guy will dissolve a heck of a lot faster because its surface area is so much greater. All right, and when we go through and we start dissolving, once we get the solute dissolved in the solvent, we've got to be able to discuss how strong that solution is. Okay, and concentration kind of allows us to talk about that. Concentration is going to be the amount of solute that is dissolved into a given amount of solvent. So basically we can say a couple things. If it happens to be very dilute, that means that there is a very tiny amount of solute. However, if it's concentrated, there's a very large amount of solute. So what this is think back to your youth here, kids. Dilute would be when you go to drink some Kool-Aid and you take a sip of it and you say, hey, that's a little weak. Okay. Concentrated would be when you take a sip of that same Kool-Aid and you say, ooh, that is sugary and delicious. Okay, so that's kind of what we're getting at with concentration. Dilute just means there's not much solute. Concentrated means there's a ton of solute dissolved in that solvent. Okay. And obviously our two pictures here kind of indicate differences. We've got what looks like a raspberry tea bag. But this is going to end up being your concentrated solution. This is going to be your dilute solution on the left. Okay, you can see the difference in the amount of solute that's actually dissolved. And we need to be able to go through and not just say, hey, it's concentrated or dilute, but scientifically put words on them. So we've got three different types of solutions in terms of saying how much solute is dissolved. Okay? Saturated solution basically means that there is a perfect amount of solute dissolved into the solvent. And what we're saying here is that every single object, whether we're talking about salt or we're talking about sugar, or if we're talking baking soda or whatever, will have a certain amount that can be dissolved into, let's say, 100 milliliters of water if we're at 25 degrees Celsius. And we're going to look into this in a little bit. A saturated solution is holding the maximum amount of solute in the water. If you add any more, it's going to start piling up in the bottom because that amount of water at that temperature cannot hold any more of the solvent, or sorry, the solute. Okay, so this has the maximum amount of solute for that solvent. Unsaturated basically means that it has less than the maximum amount. So unsaturated is saying you could add more. A supersaturated solution basically goes through and means that you have more than the maximum amount of solute. And having too much solute means that some is going to pile up on the bottom of a container. When you go through and you think back to your childhood youth when you're making Kool-Aid, and you poured all that sugar or Kool-Aid mix into the water, and you had the sugar pile up on the bottom, what happened is you were creating a supersaturated solution. Okay, it had more than the maximum amount of solute, which means that you had sugar piling up on the bottom of your Kool-Aid container. Okay, so we're going to discuss things in terms of saturated, having the maximum amount, unsaturated, meaning that you do not have enough, or you could hold more, and supersaturated, saying that you have too much solution. Now, we've talked about the idea here real quick, or hinted on it, that each specific substance has a different saturation level, or can have a different amount held in the same amount of water. And we're going to talk about that kind of on the following slide here when we start talking about solubility values. So in discussing solubility values, we again have pointed out, and we're pointing out again, that each substance is going to have a different solubility value. Basically, a solubility value tells you how much of that substance will dissolve in a certain volume of water under a certain temperature. And you should remember from a couple slides ago that if we raise the temperature, we are going to increase the solubility value. So right now, we're doing everything at 20 degrees Celsius. If we were to go through and raise this temperature up to, let's say, 25 degrees Celsius, all of these solubility values, and mind you, these are made up because I don't know what they are off the top of my head, but your solubility values would increase briefly. So maybe this would turn into I should use a different color, maybe this would turn into a 36.7 grams, and maybe this would be a 76.2 grams, and maybe this would be a 205 grams, etc., etc. Again, these are quick estimates, but you get the idea. As you increase the temperature, you should be able to dissolve more of that solute into the solvent. Okay, and what really happens here is the solute itself will stop dissolving once the solution has hit equilibrium. And what equilibrium basically is the amount of solute molecules coming in and going out of solution have been reached. And this right here, your equilibrium, is essentially your saturated solution. So in a roundabout way, what we're trying to say is if you happen to have 100 milliliters of water, I know that I can dissolve 35.9 grams of table salt into it at 20 degrees Celsius. We'll get rid of this stuff. I know that I can take calcium chloride and I can dissolve 75 grams into it. So I can dissolve almost twice as much calcium chloride into that same water as I could table salt. And sugar, I can dissolve a whopping 203.9 grams. So comparatively, I can dissolve a ton of sugar into that same 100 milliliters of water. And baking soda, it's a disappointing 9.6 grams of baking soda into that 100 milliliters of water. Now, does everything dissolve? No. I believe some things such as talc aren't going to go through and dissolve at all. So you can't get any into water. So it just doesn't dissolve at all. Now, there is going to be, if you go through and check the Wikipedia here, just a giant table of thousands of different substances and what their solubility values are at given temperatures. So whether it's 10 degrees or 15 degrees or 20 degrees or 25 degrees Celsius, there is obviously a resource where you go through and look that stuff up. So last thing we've got for today is figuring out how much will dissolve in water. And this is basically just setting up ratios. How much table salt will dissolve in 250 milliliters of water at 25 degrees Celsius? Well, if you look at the last table, which should be in your notes, you can tell me that 38 grams of salt dissolve into 100 milliliters of water. This is basically something that was given to you on the table. And all we're doing is we're trying to multiply this out by a ratio. We're trying to figure out how much will dissolve in 250 milliliters. Okay? So what you do is you go through and you do your little cross multiply. 38 grams times 250 equals 100 milliliters times x. You end up with 9,500. Multiplying those two. 9,500 here. And we'll toss this blue one right here. Times your 100x. Do a little dividing, so divide both sides by 100. And that will leave you with x equals, what we got there? 9.5? 95? 95 grams. I carried the one wrong. Yay. But you get the idea here. It's a simple set up a ratio, cross multiply, and then go through and divide out and solve for x. On a second note, let's try a second one. How much water would you need to dissolve 150 grams of sugar at 25 degrees Celsius? So we could go through and set this up again. I remember that sugar was somewhere in the 203 grams range. So I've got 203 grams of sugar. And that happened in 100 milliliters of water. So that's my initial. This is what the table tells me. Let's go through and multiply it out. How much is going to dissolve in 150 grams of sugar? Or how much water do we need for 150 grams of sugar? And so this is going to be x water. Okay? And finishing up, we basically go through and cross multiply those out. Get your 15,200x, and you're basically just isolating for x to get 75 milliliters of water.